Emilio, can you please share your screen and give your talk?
I try to share a screen. Compartir. And now let me view. It's okay?
Yes, I can see your screen.
Okay. So, yes, I'll talk on my recently published book in Springer. Those are the covers. Before last year, so end of last year, I published the first version of essentially the same book, although the English one is much bigger, but it's essentially the same idea in Spanish. It was published last year. And before talking about the contents of my book, which will be essentially my talk, I will say something about Steven Weinberg, in relation with a book that he wrote on the history of science. And, Weinberg passed away last July. He was one of the most important physicists, some people say that he had a mythic status, one of the greatest physicists, and had a profound influence. And this is true because he wrote, apart from articles and his contributions, he wrote several books, very influential: Gravitation and Cosmology, The First 3 Minutes. This is a popular book, very well known. Almost everybody in the world that has some interest in cosmology and in science knows this book. Dreams of a Final Theory, the Quantum Theory of Fields, in 3 volumes. But one important thing is that, in relation with my book, is that when he wrote a book to explain the world 6 years ago, he was harshly attacked by historians of science. Well, there are some historians of science that say simply that active scientists should not write history books. Well, Weinberg was criticized, strongly criticized by historians because he called Plato silly, Aristotle tedious and wrong about the laws of nature. Even if Aristotle, he said also that he was clear and he was serious, but well, he said that he was serious and wrong, and that Galileo was behind the times. Even the great figure of Galileo was behind the times. Why? Because he tried to use geometry instead of algebra. And Weinberg said that if Galileo had used algebra, he would have done much better. He could have done much better. Well, this approach to history is called the Whig version of history, to look at the past with the eyes of the present, and to see the science, the history of science, as being in a continuous progress. So the history of the winners. Well, to understand this better, I will just mention one sentence in Weinberg's book. I will be coming close to the dangerous ground, which is most carefully avoided. Just let me see something, because I cannot see my own screen. It is this kind of thing that I cannot see my own screen here. Well, to the danger of ground is most carefully avoided by contemporary historians of judging the past by the standards of the present. Some historians of science make a shibboleth on non-referring to present scientific knowledge in studying the science of the past. But Weinberg makes the point of using present knowledge to clarify past sciences. Well, historians say that, that you should not involve so much what you know now when studying the past. Well, you can talk a lot about this, and I have just one of my last posts in this divulgat in Catalan about this point. But summarizing, in my book, I take an equilibrated position, which is not so easy, but I use very often what I call Gedankenzeitdruckreise, mental time travel back, to place myself in the conditions of the past to understand how the people then said things, and they thought in this way, and they arrived to some conclusions that now they seem to be wrong in all cases, and how they arrived to these conclusions. I say something about this. I say something about this now, but this is an important point. So that the historians of physics, going back, they just say that active scientists should not write history books. One should take this into account. Also, in my book, I talk about luck and chance, that I think they play also an important role, and not so much is being discussed in the literature about that. But I consider that in many important scientific discoveries, luck and chance played an important role. Well, this is general. Now I'll go to the content of the book. It has 9 chapters. The first, an introduction, the awakening of cosmic consciousness. What is a scientific theory? Second, the first cosmological revolution of the 20th century, the theory of general relativity and its main solutions, the Hubble-Lemaitre law and the expansion of the universe, the Big Bang theory towards the very instant of the creation of the universe, and what I term the second cosmological revolution of the 20th century, with conclusion, bibliography, and an index. Well, summarizing a bit, my book is a short story of some aspects of modern cosmology. I place this origin of modern cosmology in the year 1912. And this coincides more or less with the moment, no, not more or less, this coincides exactly with the year when cosmologists had at disposal the necessary tools to make of cosmology a true science. Well, then in the subsequent years, these revolutions in physics occurred. General relativity and quantum physics. And cosmology made profit of this also. And finally, this allowed scholars to describe with accurate model the origin, structure, and evolution of the universe as a whole. Even more, having the theory of relativity, and also quantum physics must be involved in these extremes, we can go to the extremes, to the origin and to the end of times, and we can say something, even if these theories are not valid there. Thing that I also stress in the book, that sometimes is not so seriously taken into account. No, but we go to the origin and we talk of the singularity of the Big Bang, and so with general relativity, when we know that general relativity is not valid at these small scales, is not valid. If we go with general relativity to study an atom, we fail. Yeah, well. This is what happened here. This is advancing too much, no? But, well, we can say something about these extremes, yeah? And in the book, also I deal with this point. Well, the first chapter of the book is devoted to the awakening of cosmic consciousness. So I start from the very beginning. Yeah, this issue lies beyond the scope of the book, really, because I would need another big book in order just to explain this point. Yeah, but, well, I make a summary. I am not a specialist at all in that, but you know, just looking at the sky, about us only sky, you may say I'm a dreamer. John Lennon and Yoko Ono song, Imagine. Yeah, we have to take into account that our ancestors, when the human being started to think, yeah, to be conscious of himself or herself, yeah, when they started to be conscious, they should start also this cosmic consciousness, because we have to remember that they had as roof, they had the sky. In the nights, they had the sky as roof. So when they started to be conscious of themselves, they had to be already conscious of the world, the universe surrounding them, by looking at the stars. So this is impressive. Yeah, this is my first concept. This is what I call the awakening of cosmic consciousness. When could this happen? Well, this first chapter has this first conscious knowledge was of geometric nature, the oldest proofs of art and mathematical reasoning, and the first concepts and models of the cosmos. Those are treated in this first chapter. And the conclusions with respect to this first point are that the capabilities of hominids evolved much more gradually than it was thought 50 years ago. 50 years ago, in the 70s of last century, it was thought that 50,000 years ago, there was a sudden change. And so, more or less, suddenly, this was a dramatic genetic change that allowed humans to be able to think and communicate. Now, they think in a very different way, that the capabilities of hominids evolved much more gradually than it was thought in those years. Second point, it has been shown, it has been more or less proven that Neanderthals and their common ancestors probably communicated orally with the ancestors of Homo sapiens. And this would bring the first rudimentary expressions, oral expressions, to over 2 million years ago. And also, it has been seen by different means that 800,000 years ago, there was also a change. So the stone tools of 2 million years ago, the old Dubanian, the old Dubai Gorge, and the tools of 800,000 years ago, they are quite different. The first are very primitive, and the seconds involve what many consider that they had, that the mind had to have some geometrical abilities already in order to build just these stone tools. Well, also very large number of simple stripes on shells, but with recurring patterns, those as here, you know, this kind of patterns are recurrent in many different places, in many different conditions, on many different objects. Yeah? And now the oldest ones that are so clear are 73,000 years old, which are those in these stones here. So those doesn't prove nothing, but they prove that they have some kind of geometrical concept. They have some kind of geometrical concept, and this is what we can more or less conclude, that probably they have these capacities. And these capacities, even if we only trust the proofs of 73,000 years, these proofs, and don't go to the older proofs of this stone axis, we still are tens of millennia before, graphic symbols were used in order to write sounds, names, and languages. So this is something to start. Of course, this is, you may say, this is not so much with cosmology. Yeah, but as I say, when my idea is that when humans started to think, they should start to think of the universe. This is the idea, you know. I have no proof of that, yeah, but it's my idea that is reflected in the book. The second chapter is about what is a scientific theory. This is already more serious. I do a little history of that, then I consider Galileo, Newton, Leibniz, and give some illustrative examples. Those things I have explained previously in other pizza seminars, so that some of you have heard me talk about this. A scientific theory, to summarize, yeah, because here I have to summarize very briefly everything, has two parts, which is the laboratory part, or direct observation of nature, and the law, the explanation of these laboratory or observational results. And the two parts are equally important because we have examples, important examples, where we have only one part. And two examples are those here. Supersymmetry is one example. Supersymmetry is such a beautiful theory, starting with Weinberg and ending in the last the last part of the chain by myself. Consider that supersymmetry must be true. You know, it's such a beautiful theory that it must be true. It cannot be wrong, but we have no proof of it. There is no experimental proof, no laboratory proof of supersymmetry. So supersymmetry has only the second part. We have the theory, we have the extremely beautiful theory, but we have no experimental proof. And on the other side, we have dark matter. Dark matter is just the contrary. We have lots of data, big amounts of data, more and more precise. And some of you know much more than me about this. Yeah, lots of data which are more and more precise about the distribution of dark matter in the universe. But we still do not have the theory. Here we are missing the theory. Of course, you may say, no, there are theories. Of course, there are too many. There are too many theories. So this means that this is not universal theory, that everybody understands that this is the explanation of dark matter. Maybe there is no dark matter, still there is the possibility, you know, that you modify gravity and you avoid the existence of dark matter. Well, so it's not clear at all. Yeah. So we have a big amount of data, but we don't have a scientific theory yet. Yeah, yet. Well, the third is devoted to what I identify as the first cosmological revolution of the 20th century. So I start with how was the universe 100 years ago? How was it considered to be? Until the appearance of Henrietta Leavitt, Vestus Leifer, then that they established what, so with the measurements of distances and velocities, they could establish the necessary tools in order to make of cosmology a science. Then I discussed the great debate of 1920 on the scale of the universe, the concept of the island universe discovered by Edwin Hubble and Ernst Öpik. Well, to repeat, yeah, when were scientists in the position to describe the universe as any other physical system? At large scale, this is the description only at large scales, of course. To describe the universe, you can describe at many and many scales. And I am only addressing the question of the very, very big scales, the largest possible scales. So masses, positions, and velocities of points. This is what you have to describe. So we have a point system. The physical system is of points, because at these large scales, what we have is a collection of points. And we have to determine masses, positions, and velocities, and to represent them in phase space. Well, this occurred in 1912, because in 1912, it was the last paper Leavitt had been producing results the years before. But in 1912 is his really last paper on this, the most important on this, on her law, that discovering the Cepheid, the Leavitt's law for Cepheid variable stars, the relation between the period of variability, and the luminosity, intrinsic luminosity of the star, And in 1912, also, Vesto-Slipher started taking red shifts, in particular of the Andromeda galaxy. Well, so I consider that this year, because of this, because for the first time in history, calculating distances and calculating velocities was available. And of course, they make subsequently, as cosmologists make use of this, in order to change our vision of the cosmos. So I consider this as the beginning of modern cosmology. So those here, Slipher, Leavitt, and also Hubble, are the ones who produced at the beginning this revolution. Henrietta Leavitt obtained this period luminosity relationship, a linearity dependence of the luminosity versus the logarithm of the period of variability of Cepheid variable stars. So the standard candles of the epoch. Slipher in 1912 started to obtain the first radial velocity as a redshift, as a Doppler shift, as optic Doppler shift of the Andromeda galaxy. Then he obtained subsequently more and more. I won't discuss this because I don't have time here. And then it came Hubble, who made use of Leavitt's law, and identifying a Cepheid star in Andromeda, he could calculate the distance to Andromeda. But still nowadays, many people forget, even Weinberg and all, everybody forgets that Ernst Öpik, 2 years before Hubble, calculated the distance to Andromeda much better than Hubble, not using Cepheid variable stars, but using the other approach, which is much more, with the hypothesis that all these galaxies should be similar, and similar to the Milky Way, and so that the luminosity, the intrinsic luminosity of Andromeda should be proportional to the mass, of this nebula. It should be proportional to the mass of this nebula, because at that time it was called a nebula, spiral nebula. So should be proportional to the mass of the nebula, and the mass he could determine, the mass gravitationally, he could determine the mass, and so he obtained a value for the distance from there, from this intrinsic luminosity and the luminosity that we see from here, and that was much better than the number obtained by Hubble 2 years later. Well, anyway, the 4th chapter is devoted to the theory of general relativity and its main solutions. Einstein's general relativity, the fundamental principles of general relativity are analyzed with some care. Then I I talk about in the book about the Einstein approach to the universe in 1917, and the first solutions to Einstein's equations, Schwarzschild black hole solution, de Sitter's universe, and Friedman families of solutions. Well, the first cosmological revolution had three important milestones. The first was finding that the universe was much larger than it was thought in Einstein's time. That it was thought that it was reduced to the Milky Way. The second is presented in this chapter, which is that the universe was expanding. Before, it was thought that the universe was static, and there were very, very good reasons. And this is one example of setting ourselves in the past, with what they knew in the past. They thought that the universe had no origin, had always existed. The universe had always existed, that it was static. Why? Because any physical system, under very general conditions, any physical system, given enough number of time, a large enough time, evolves into a static condition, static state. So the universe that had infinite time to evolve should be, of course, how could be different? It should be static. And this was extremely reasonable for the time. Well, about the distances, I didn't say anything now today, but calculations of distances is the most difficult thing in cosmology. The most difficult thing is calculating distances, the distance scale. It has been along the whole history of humanity the most difficult thing, and it is still today, still now. As you know, some of you know this much better than myself. It's still now the calculation of distances. So at that time, everything was in the Milky Way. So all these nebula that by the thousand they had been already discovered, they thought that they were in the Milky Way. So the universe was very small, reduced to the Milky Way. So, and those were the changes. Those were the three changes to realize that the universe was an island universe. There were many Milky Ways. There are many galaxies. This was one thing. The other, that the universe was not static. No. It was expanding. And finally, that the universe had an origin. Those are the three milestones that are discussed in subsequent chapters of the book. Well, I want to refer here to this because I reread this paper by Weinberg, which is very beautiful. Einstein Mistakes. It was published during, the World Year of Science, 2005. It was published in Physics Today, so already some years ago. But now, by preparing these things, I reread this, and it's very nice. It's a very nice paper. I recommend if you didn't read it. This is just to say that in my book there are only 4 or 5 equations. This is another point. They didn't allow me to put equations. But you know what Hawking said, that each equation of the book divides by 2 the number of readers. Each equation that he put in the book divided by 2 the number of readers. Well, I have put 4 or 5 equations. This is one of them. Is very important, very necessary to explain one of the most, or maybe the most difficult point to understand about general relativity for people who are not experts. That pressure goes together with energy and mass and energy. So the pressure are not a pressure of a fluid or something, no, it's the pressure of space-time, of the reference system, of space-time pressure goes together. And in order to give some arguments there, it was for me absolutely necessary to put an equation of this kind in order to show this, that you can trade one for the other. Well, I cannot be more explicit, I cannot be more explicit. Chapter 5, the Hubble-Lemaitre law and the expansion of the universe. I start by the considerations of Carl Lundmark and Carl Wirtz, two great astronomers who tried to obtain Hubble's law. Those two tried seriously to obtain Hubble's law. So they almost found, they tried to find a proportionality law between distance and velocities of galaxies. Yeah, distance and velocities. They did not succeed. And the reason they did not succeed is that their data were not reliable enough. And why they were not reliable enough? Because they didn't use the standard candles. Yeah, so these Cepheid stars as Hubble did. Yeah, they didn't use this as Hubble did, and this is one of the main reasons. This is one of the main reasons. Carl Lundmark argued as opaque in the sense that the luminosity should be proportional, intrinsic luminosity, to the mass of these galaxies. And Carl Wirtz argued in a similar way, making the hypothesis. They made the hypothesis, that all galaxies were so more or less a standard. And here also that all these galaxies were more or less a standard, in the sense that, and so standard, Wirtz thought that they were more or less the same size. More or less should be the same size. So that he connected luminosity, intrinsic luminosity, with if they were the same size, with this, and they failed. Yeah, Georges Lemaitre was the first to understand Hubble's law. So I discussed Georges Lemaitre, I discussed Hubble's law, the interpretation of Hubble's law given by Lemaitre for the first time, and the general acceptance of Lemaitre's work, because Hubble's law, even if people started to know the contribution of Lemaitre, still Hubble's law was named Hubble's law until 3 years ago. Until 3 years ago. 3 years ago, in the meeting of the European Astronomical Society in Vienna, it was renamed to the Hubble-Lemaitre law, recognizing finally the contribution of Lemaitre. Lemaitre did nothing, so to say, original discovery, because he didn't take any data, any distance, he didn't calculate any distance, he didn't calculate any velocity, and the thing, he was a theoretician, and the thing that he really did was to obtain a solution of Einstein's equation for the universe, to describe the universe. But this solution of the Einstein's equation that he obtained, it had been obtained before by Friedman, so that finally his contribution, only contribution but important, was to understand everything, to connect all data with the theory, and to really make the scientific theory of the expansion of the universe. So it is claimed that it was in many places. Everybody claims that Edwin Hubble discovered that the universe was expanding. Yeah, discovered. Edwin Hubble contributed enormously to the discovery, that the universe expands. But he only contributed to the experimental part, to the observational part, He obtained the law, this proportionality between velocities and distances, the law, but the empirical law, the observational part. He, all his life, he was against the idea of the universe expansion for different reasons I cannot discuss. He had also reasons. Yeah, one can say why he always argued against this. He had reasons. One of the reasons was that if you consider that the universe had an origin and the universe had been expanding, according to the Hubble constant that he calculated, that he calculated even with some reformulation some time later, the universe was only 3 million or 2 million, I remember, maybe 2 or 3 million, so to say. It was 2 2,000 million years old, 2,000 million years old. And so it had no time even to create, the Earth, and so there were problems. But the problem was that his calculation of the Hubble constant was off by almost an order of magnitude. But he had strong reasons in order to go against the expansion of the universe. And all his life he was defending that as many, not only Hubble, all physicists, all cosmologists for many years, they didn't understand, they didn't buy this expansion of the universe, because they understood that these redshifts obtained by Slipher, the redshifts, they were not due to the Doppler effect. They were not due to the Doppler effect. They could come from a tired light effect, so that, the photons, they were losing energy on this way to the Earth. They were losing energy. This was also very, very reasonable. Very reasonable. So, and there were different theories around that, not only one. In general, this is called the tired light theories. That this was losing energy, and this was also proportional. This energy loss was proportional to the distance. So it was natural that this redshift, that the redshift was bigger when the object was far away. But this had nothing to do with the velocity of the object. What had this to do with the velocity of the object? No, it was losing energy, and so more distant objects, more redshifts, because it was losing energy. So this is one of the arguments, and many of these arguments that one can understand only by putting yourself in the conditions of the past. Can you understand how all these people did not understand, did not buy this expansion of the universe? Even Einstein for 10 long years. Also, another effect that was involved was the de Sitter effect, also that was used with the de Sitter equation in order to match many of these observational data. Okay, so once we understand this, we go to the Big Bang theory. I make in this chapter some considerations about dark matter. Then I talk about Fred Hoyle, the Big Bang, George Gamow, the cosmic microwave background, Alan Guth, and Starobinsky inflation. I have to hurry. I have to hurry up because I don't have time in order to discuss the Big Bang. You know that the Big Bang is one of my specific points where I put more effort, because it's so badly explained, in the popular literature. In many places, it's so badly explained, the history of the Big Bang. So when Hoyle said Big Bang, what he was meaning, excuse me. This is so badly explained, and I put much effort and time in order to explain this, and this is done in my book. I don't say anything more. Also, I talk about inflation and the miracles of physics, #1 and #2 by Alan Guth, that taken from his lecture at MIT. And then I go towards the very instant of creation of the universe. In this chapter, the Big Bang cosmological models are discussed, because the Big Bang is used in order to name different things now. Attending to the origin of the word Big Bang, the translation, the present translation of Big Bang would be inflation. Inflation. So this is the actual translation of the word Big Bang. So when Hoyle said Big Bang, he meant inflation, what is now called inflation. And he defended this during his whole life, yeah, that the inflation was nothing else than what he had said when he said Big Bang. And no, but you can see that he said these words. I don't have time in order to put them here. You know, I have time to spend more on that. But so the actual translation of the word Big Bang pronounced by Hoyle is inflation. But now Big Bang is used with different purposes. Big Bang cosmological models, as you know, the different Big Bang cosmological models, and the Big Bang singularity. Now, usually, Big Bang is associated mainly to the singularity. When they say Big Bang, and everything starts from Big Bang, singularity. Then comes inflation, which is the real Big Bang, and in the original, but now is the Big Bang singularity, which even before inflation. Before inflation, there is the singularity. I don't have time in order to discuss this, but this is also, I explain about all the different singularities, ending with the modern version of the singularity theorems of Hopkins and Penrose, which is the Borde-Guth-Vilenking singularity theorem. Because in this, they include the expansion of the universe, and they include inflation. They include inflation, that the universe is expanding, and also the period of inflation. Is still the singularity theorem, Penrose singularity theorem, is still valid when we include in general relativity, we include inflation, and we include, and they prove that, yes, and it's not exactly the same theorem, but they generalized, they extended the theorem to this point, but they didn't see that the theorem breaks down. Well, maybe more specialists can explain more about this, but this theorem is still very popular for some people. For creationists, they approach me about this theorem because creationists, they think that, that this is still, there's the origin, looking for the origin of the universe, and they give enormous value to this theorem, I can tell you. Well, 8th chapter is the second cosmological revolution of the 20th century. The fact that an expanding universe satisfies Einstein's equations unexplained, this is only just in order to put here something that appears in my book, appears in my book. Easy explanation. Sometimes a person going to the shop, here the Le Petit Prince appearing in the explanation. So I try to be as much pedagogical as I could be. As much pedagogical as I can. So if there is no acceleration in the expansion, if there is only uniform expansion, you can explain this easily with Einstein's equation, with the solution of Einstein's equation. You can explain this with the Little Prince. If the Little Prince throws a stone from his small planet, this stone will never come back. Because the planet has this small mass, and he's strong enough in order to throw the stone far apart. Of course, if we throw the stone from the Earth, it will come back. So these kind of arguments, in order to say that if you gave an impulse, an initial impulse, then the universe can expand forever, or maybe not, or maybe then will contract back. These arguments that were the real important arguments of cosmology, before understanding the acceleration of the universe expansion. Those were the main arguments. What was the critical? The universe was critical, over critical or under critical. How was those were the arguments? No, this is explained in a few words with these kind of examples. Here, in order to explain the acceleration of the universe expansion, of course, you need here some extra aliens, something that we have not found yet, in order to explain the acceleration that is continuously accelerating the little brain. Well, okay, this is just to... Well, an important point about the second revolution. The second revolution cannot be reduced to the discovery of Rees et al. And Perlmutter et al. Using the supernova as standard candles, because some 15 years before that, already the first models of a non-vanishing lambda, had appeared. And even Enrique Gazzaniaga and Pau Fosalva and myself had been playing with these models, not the only ones, and not the main ones, but many people had been playing with this kind of models. So that this implied already that the universe expansion should have some acceleration, because putting a non-vanishing lambda is putting an acceleration. Yeah. And also, of course, those, and so these discussions were already around. And also, after these discoveries of the 98, 99, after these discoveries, still for some years, not everybody trusted these discoveries, and they needed a confirmation afterwards. So this was not the only thing. And these confirmations came from very different points, and there were a strong controversy for some years, at least for 6 years. I count by looking at these. The main papers were these supporting results were published on the CMB, early galaxy formation, nearby galaxy distribution, the cosmic baryon, etc. No, and always now the point is, the big question remains: what is the physical baryon acoustic oscillation? I meant baryon acoustic oscillation. I cannot read part of my screen, So, okay, and this was. It took some time until this was accepted. The conclusions. In order to summarize, conclusions, the book has a bibliography of some 250 references and an index with some 600 items. In the conclusions, the first revolution, I frame it in 1912 to 1932. From the discoveries of Leavitt and Leifer to those of Hubble, including the theoretical advances of Einstein, Friedman, de Sitter, and Lemaitre. It came to its peak, it had a peak in 1929 with Hubble. The same as in the other case. There was a peak here. Also, Hubble pretended to be the only discoverer of all this. In 1920, with publication of Hubble results confirmed in 1931, but eventually came to its understanding, acceptance of the expansion of the universe in 1932 with the work of Einstein and de Sitter. But even then, even if I put this 20-year interval as the gestation of the first revolution, still had to wait to the elaborate formulation of the Big Bang model, which occurred later, much later. The definitive test of this through the detection of the cosmic background radiation, and still a major reshaping inflation in order to understand the Big Bang model, because it had so many problems, which all would only arrive 50 years later. So, you can consider that the expansion of the universe was clear already in 1932, and this is what I put here, you know. But still things go on, you know, and these years had to pass, yeah, for the completeness of this revolution. The second revolution occurred, as I understand it, in the period of 1985 to 2005. Exactly 20 years also. Yeah? I already said the reasons why for this. It had the peak in 1998-99 with the supernova results, but full confirmation came later. Yeah, and the similarities between these two revolutions are really remarkable. 20 years in each case. Yeah, the definition of the revolution, 20 years in each case. Also, in each case, there were somebody, some leaders who claimed all the merit of the breakthrough, so to say, exclusively. In the case of Hubble, it was clear. And all his life, Hubble, all were results from the Mount Wilson Observatory. You mentioned also, you know, not only Hubble, but Hubble and his collaborators and Mount Wilson Observatory. In the second case, it was this, that, oh, the supernova observation, this was all, the whole thing can be explained with, no. These claims are not sustained, as I write in my book. I must thank very much Enrique Gazzaniga for making my mind clear, making me think about this second revolution in proper terms, because, you know, I had not digested all this. Yeah, when writing the book in Spanish, I had not digested all this part, because, you know, writing the book, I hear sketch only things. You should read the book. It's much better written. So my writing is much better than my oral expression, in 2 words. You know, that is much better written than what you get from my expression today. Yeah, and I thank Enrique so much for that. I thank him in the book already. The story was much richer and complex also here. 20 years, but all the time. Theories, cosmological theories, are evolving, and there are many crucial contributions to this. But, well, more or less, and this is maybe sketchy. These approaches are maybe sketchy, but you should proceed in this way. You have no choice, in a way. You have no choice, because when you compare when what happened to the other revolutions, when you compare with the other revolutions in history, the most famous French Revolution, it cannot be reduced with the events of a single day, of the taking of the Bastille, cannot be reduced to this day. No, this is different. No, of course not. It's a long contribution. It's extensive in time, and with different contributions, and sometimes even they are not coherent. Yeah. Nevertheless, in the end, they produce great transformations in the behavior and organization of peoples and societies. If we talk about the scientific revolution, famous scientific revolution that took place in what is called sometimes the long 17th century, it comprises from the 16th century, when first investigations in anatomy and astronomy with more or less modern techniques were performed for the first time in history, and ending with Darwin, that belongs already to the 19th century. You know, so this is the long 17th century. You know, this scientific revolution, you know, it's ongoing, and the main thing is that you can only recognize this from the perspective, from our perspective. We recognize the revolutions. Cosmological models are continuously being reshaped. And with this, I come to the real conclusion in my last page. As astronomical data accumulate. But one thing remains clear. that when we look in perspective, the whole past century, from the end to the beginning, and when we look at it from this scope with open eyes, we realize that astronomical observations throughout the century had an extraordinary, almost incredible implications that change our vision of the universe. From being small, static, immutable, and eternal, it became enormous, expanding, and with an origin out of nothing or almost nothing. This is what I named the first revolution. Then we also learned that this expansion accelerates without stopping, thus creating a mystery where before almost complete, at least for a while, for some years, for a while, complete certainty seemed to have reigned before. And this is the second revolution. For me, those are two really impressive revolutions and two of the greatest discoveries in human history. And with this, I finish. Thank you very much. Okay.
Wow.
Now, how I está compartiendo. Deja de compartir pantalla.
Yeah.
Okay. Yeah.
Okay. Thank you, Emilio. Now, in fact, we are running out of time, but I think it's good to have a few more minutes to ask if there is any questions, comments.
No, of course, it's difficult to say something about this, you know, because it's the presentation of a book. But, well, my points are that I recognize this, I call these two revolutions, and I didn't see this, that they were called in this way. I don't know if you heard about them under these terms.
Well, if not, I have a question in general. Carlos, I don't know if we have tried or if we have such idea, if probably we can split it into two seminars in 2 weeks. I don't know if it's possible or we have considered this idea.
Carlos is in a call with Sedeti right now. He sent a message. He sent in the chat.
Okay.
So he cannot answer.
Uh-huh. Okay.
Okay. Can I say something?
Yeah.
This is Abu Bakr.
Yeah, please.
Yeah, thank you so much for your overview, and it's really amazing book, it seems. I just like the idea when you mentioned the consciousness, and like you link it with the fact that the very thing that we start is to link it with the universe. So could you just like comment on this point? And I would like to know, like, what is your personal view about the consciousness itself?
Well, for me, it's, you know, I am not an expert at all in that. Yeah, I made the effort of reading some references here and there, you know, documenting myself, but not precisely. I didn't find references about the cosmology. So this idea of the sky, to look at the sky, this was my own idea. No, this was my own reflection. Yeah, that all. You know, this is something that it occurs to me sometimes. Yeah, this is some thought that I had some time. No, to think when a human started to think, started to be conscious. It's difficult to describe this. Yeah, it's difficult to describe. But I thought that the influence of the sky, of looking at the sky, must be important. because they were not all the time in caves. Of course, they had shelter in these caves. But then, in other times when they lived in the savannah, they had the sky the whole night. And so, but I didn't find this, I really didn't find documentation supporting this, I really didn't, this was my personal idea, and I wrote it while writing the book, that you start to think what I can put there, and that it occurred to me. The other thing is about these stone tools and these kind of things and geometry. And for me, as I am also a mathematician, and for me also to prove that mathematics and mathematical concepts were even before philosophical ones, it has been a point also. I have some, I have some papers, some writings on that, that the geometrical and the mathematical thing, the mathematical thing, the conscious of the one, of the two, and the strips on this geometry, those concepts were even prior to any, so are very primitive. In my mind, they are extremely primitive concepts. Even before some, even rudimentary philosophy was there. And the same, I think, about this cosmological concept, but just the conception of the universe, you are in this thing, in this universe, as a conception, without any other idea, no specific idea. But this was my point, that this must be very, very, very primitive.
Okay, thank you so much.
You're welcome.
Okay, I don't know if we have any other questions. Well, if not, let's stop here. Emilio, thank you for your great talk, and thank you all for your attention.
Okay, thank you.